All right. Hi, I'm Peter Booth, and I'm the substitute Randy Bush for this. I'm told I'm a little too tall for it, but it'll work out. So I'm going to be presenting on using the DNS servers to measure the flapping in Anycast, and how Anycast can highlight certain forms of routing instability. Been doing this work with Randy, and we've been helped out by Lucy and Joel and all these people, and of course many of you, although not more than half of you, because we got 150 participants in total, and there are slightly more than 300 of you. So, why do this? There was a VeriSign presentation in the last NANOG, I believe, on the life and times of JRoot, and they reported non-trivial routing jitter, and concluded that you should not run Anycast do not run Anycast with stateful transport. But for a decade, for a long time, we have had reports of successful delivery of services over Anycast. So there's clearly something going on here when we have these two things disagreeing, and that's a nice, fruitful area for research, which is good because I'm a grad student and that's what we're supposed to do. All right, first things first. We contacted the folks at VeriSign, and we found out which routes were flapping and sort of asked them for their data, and they sort of obliged us, and we worked with it a little bit. And we watched the relevant routes flap using bgplay, but in this part, the problem is that bgplay has there's a few issues with bgplay where you can't quite, in certain instances, it's really, really hard to understand what's going on because all the Anycasted clusters appear as one point because they look like one thing in BGP, and that's the whole point of Anycast. So this tool, which is great for some things, was very difficult for us, and so we designed an experiment that you guys participated in to check out how common all this behavior was and to see what was going on and whether anyone was affected. Our experiment, we sent out emails to NANOG and SANOG and a bunch of them, and got a multitude of hosts. As I said, we had 190-ish unique IPs reporting and 140-ish unique ASs reporting. We sent, and we got all these people to run our collection script, which did the following. It looked up its externally viewable IP address, and then sent a UDP query every 2 seconds to each Anycasted root CFI-JKM, and then sent a TCP query every 20 seconds to each Anycasted root, and then we emailed the results to a central server. So why 2 and 20? You got to be suspicious every time you see numbers. That's because the VeriSign people reported route flapping, or at least cluster switching, on the with frequencies on the order of 5 seconds. And if you want to measure something at 5 seconds, you have to sample it twice that, so 2 seconds. And then TCP, because you want to be nice to the roots, and so we backed off there. The query looked exactly like that. We were digging at each root server for chaos TXT, because all the root servers have agreed that to put in the chaos TXT field the actual name of the box that responded to the query. So it looks just like all the others in every other respect, except that one field, which we get to use to distinguish them. So what did the sample script output? So here's what it looked like. The externally viewable IP address, 192.87.109.158. And then as you go through this script output, you can actually see the timestamp, and then what root we were talking to, what protocol we were using to talk to the root, and which root server responded, what was in that TXT field. Often this, well, not that often, but sometimes this field was blank, indicating a no reply. So now, before I continue, I have to make a disclaimer. This is about routing. We're using the DNS servers to study routing, not using routing to bag on the DNS servers or something like that. And we did use a regular expression on each host name into a cluster identifier so that we didn't have any load balancing issues with the cluster, and we got all those regular expressions validated by each root op. So now, why is this what you're about to see happening? Well, it's probably caused by eBGP IBGP and IGP, and some combination of those two, because it really does seem to be a routing type phenomenon. And just for posterity, here are our results. But these are relatively crappy to read. It's just, you know, you might want them on the website for you, so later you can go like, oh, this is how it worked. So we sent 117 million probes and saw switches to various routes between clusters, and there are percentages of failures and all this other good stuff. The interesting thing to note is that generally TCP failed more than UDP, just like our intuition would expect, except F, which responded, which they were basically the same. And there you go. But these aren't very edifying. What's more edifying is when we break it down and look at some things like the mean time between switches. All of a sudden, we can see really, really clearly, because we also distributed our test script across the Planet Lab, across a huge set of Planet Lab nodes, is that Planet Lab is much more stable than the Internet. The mean time between switches in Planet Lab is 2.2 hours. The mean time on the Internet for over all the hosts we measured is 14 minutes. So this means that if you're doing a study on Planet Lab, you have to be careful about generalizing, at least if you're talking about routing stability. And the standard deviation for the Internet, much higher. So there's a much wider variation on the Internet. And just because if you show someone this mean and standard deviation, you should also show them the median. The time between switches, the average time between switches for the median AS is presented as well, but you can care or not. It really is a coincidence that they're both 1.4 hours for Planet Lab. So there's this wide distribution. I mean, 14 minutes plus or minus 2 hours? No, definitely plus, but Planet Lab is much more stable, and there's a large variance on the Internet. Okay, so now we look at some ASs in specific, some nice cases to track what's going on. And some things, and what we're going to do is we're going to make frequency graphs. So we look at each AS and we look at what they saw for the routes, for the root servers, and we say, okay, well, if you see one root server and you get the same root cluster, and then you get a different root cluster, we measure the time between switches. And then we make a graph of all the various times between switches we saw, and we make when we quantize these into buckets, and so we can hopefully get a sort of a frequency or a distribution of what's going on. So sometimes the changes for every root track together. That is, sometimes when you see a different cluster at C, you also see a different cluster at F and I and J and K and M, which intuitively to us sort of indicates IBGP or IGP churn, because what you're seeing possibly, and this is, you know, as it says, rampant supposition and the subject of ongoing investigation, we suspect that what's happening is you are switching between exit points on a geographically distributed network. So all of a sudden you get this exit point, and you're getting and you see this view of the network, and then you get that exit point, and you see that view of the network, and you're just switching between them. Sometimes they don't track together, indicating that there's changes possibly farther down in the stream. And sometimes they do a little of both, which, you know, makes analysis always more difficult. So here's a sample AS. It's sort of a median AS, if you will. And one thing that, you know, keep track of the y-axis, and just here we go. So this AS saw a lot of switches that were on the order of between about 10 seconds and a minute. So that looks log scale about 30 seconds. So they saw a lot of switches that happened on the order of 30 seconds. Now, not a whole lot. I mean, we sent out 748,000 probes from this AS, and we saw, you know, 20 switches sometimes, 20 switches at that frequency for one route and 12 for another. So the total switches seen is, of course, the area under all these curves, and there's different curves for each one. So let's now look at a good one. Hooray, good. This one, we sent out 151,000 probes and never saw a single switch. Nice and stable. Then we see things that switch a little bit more. Keep track of this y-axis. So here we saw 70 switches, and they're all tracking together and going a little kooky. So that's, you know, possibly IGP, possibly IBGP, or possibly just, you know, we're wrong. But it's definitely a real effect. And, we get the ugly. So, it was 70 before, it's 250 now. And it gets a little worse because it keeps going. And that is 25,000 switches for one particular route, indicating that we have some sort of clear route flapping going on. So, what's happening? So now, one question is, does this matter? So let's talk about failures now. How many failures did we see from each route? Because if we see failures from route, then we'd be seeing interference between control plane and data plane, and that'd be cool. So if you'll recall back to that one where I presented the raw data, TCP failed more than UDP did as a percentage. And we don't really know what's causing these failures. If you look at the frequency distribution of these failures, sometimes they're Poisson, indicating that the events causing the failures are independent. That's not helpful, but it's at least something. And so the question we want to know if there's switches and failures are correlated. Do ASs with a greater amount of switching see more no replies? But let's first compare the two protocols, TCP and UDP. The failure rates were often really, really distinct between the two of them. This is the same AS over the same time period seeing different failure rates for different routes. The scale on the graphs is, a little bit more. One goes up to 1400, sorry for the pixelation, and the other one goes up to 3500. But aside from that, it's not too bad. They're not too distinct. And if you look at it, we're seeing dramatically more no replies, or not seeing dramatically more no replies from K-route. And if you look at it, there's still a green blip on that right one on the TCP graph, but it's completely dwarfed by K-route just not being into responding to TCP replies. So same AS, same times, very different behaviors because of different protocols. That's interesting. Now, what do we care about? We want to know if switches and failures happen together, if switches cause failures or failures cause switches or something. So how often do they happen together? So to find this kind of thing, you calculate a correlation coefficient, which is a number that ranges between -1 and +1. And if it's 0, then there's no correlation between the things. For example, UDP and iRoute saw no correlation between its switches and its failures. Now, if it's -1, that means that the two things are negatively correlated. When you see more of one, you see less of the other. And if it's if it's closer to -1, you see that. And if it's closer to +1, that means they're positively correlated. That is, if you see more switches, you'll see more failures. Or if you see more failures, there are probably more switches. And looking at our graphs, you see that in general, TCP is slightly more correlated, switches and failures, just like we would expect. TCP TCP switches are more correlated with failures. You switch out in midstream, you're going to see failures because you're talking to one cluster, you're routing switches, and all of a sudden you're sending the middle of a stream to some random cluster who doesn't know what you're talking about. So you're not going to see anything. And that's going to manifest itself as a no reply. So all of a sudden we're back to here, and we know, and so here's the scatter plots for all this. And so let's have some take-home lessons from all of this. Oh, thank you. So let's have some take-home lessons from all of this. Take-home lessons. Routing weirdness seems to affect Anycast kind of disproportionately. And Anycast is a really nice tool for watching routing flaps change. That's kind of neat. Planet Lab is not the same as the internet in terms of routing. Oh my God, this is big news for us academics. We really want it to be the same because it's so much easier to deploy things on Planet Lab than to ask things of you. Some people caught that. Most ASs are okay. But when things get bad, they can be very bad, and we saw a much wider distribution of good versus bad on the internet than we did on just Planet Lab. UDP and TCP probes fail differently. So generalize it, you don't really want to generalize from one to the other. And for everyone who participated, your autonomous systems data can be found at that or that URL, depending on which side of the room you're on. And you can check it out yourself and see how you failed and how you switched as measured by UDP, TCP, by both UDP and TCP to all the routes. So I'd like to also thank everyone who did participate for their participation, because it was really actually pretty neat to have new data coming in every morning to analyze and parse and mess around with. All right, and if there are questions just about like, what did you say, like sort of understanding type questions, you're welcome to ask them now, but otherwise we're going to have Daniel Karenberg come up and sort of continue on this theme. Uh-oh. So, there's one.
So I'm Mark Osters from VeriSign.
Oh, hi. Thanks for sending me that thing.
Oh, you're welcome. You're welcome. So one of the things I noticed when we were looking at some of this data is that there seemed to be a lot of sort of correlation between the high sort of frequency switches and area of the world. I was wondering if, for example, some of the high frequency switches we saw came from like India. Another one took place in Australia. And I was wondering if you saw something like that as well.
I haven't done any strong geographic analysis. I was trying to bug people for good ways of finding out where things are located. I keep asking people, I think I keep asking the wrong people, because I ask people who do weird things with BGP and assignments, and they're like, dude, you can't know anything because it's BGP and you're just going to tweak the knobs, and I just hide all that information from you anyway. So I haven't done any geographic analysis, but I do agree that everyone who has looked at these data has said that the things that were more flapping were also tended to be on the edge of the network, tended to be edge-ish.
Yes, so that's what I saw as well. The other thing is that the point of the talk, just to kind of reiterate with their life and time, is Jay, which all this kind of originated from, is that it's fine with UDP sort of DNS queries, but I knew of a lot of people that were thinking about using Anycast with stateful sort of transport mechanisms. And that I wanted to caution against, say, hey, look, we got this little area that we need to look towards here if you want to have a global sort of footprint for these sort of services.
My name's Eric Osting with Internet Network Services. I was wondering if you had done any work to try to take problems that were happening with the root services or the root servers out of the equation, to like sort of subtract that problem from it. For instance, putting a device that's close and could talk to a particular root server near it so that you could.
I will tell you that we're right now building up boxes to deploy to various locations to slurp the IBGP, IGP, and eBGP feeds for a particular area while we're running these probes at the same time to hopefully do exactly that. But that's still in the working on it stage. Does that answer your question? So that's an attempt to factor out DNS servers having issues, but at the same time, I think Daniel's going to be talking about DNSMon and another way of doing that. So.